So, what did we do until now?
We talked about lattices.
We talked about mathematical definitions of lattices. So, we decided that basically a lattice is characterized by the lattice vector. And if we have something that all the points follow this vector, of course, with different n1, n2, and 3 for each point, then we have a lattice. If we have a structure that is repetitive but not for each point, so we create a brevet lattice. Now, we gave some examples of lattices: simple cubic, face-centered cubic, base-centered cubic, FCC and BCC. Usually I give a few more examples, but since this semester is short, anyone who's really interested in seeing the whole plethora of different lattices, no problem finding it on the net. The only thing I'll just mention is a diamond lattice, which is actually two FCC lattices, with one is slightly moved from the other. This is important because a lot of important materials follow this lattice: carbon, silicon, germanium, all of them have this diamond structure. Okay, then you have plenty others. Okay, in physics, when we have something in real space, what do we do with it?
Approximately. You transform, if it has to do with waves, you transform it to Fourier.
Right, if it has to do something with waves, you perform a Fourier transform on it. And since lattices have much to do with waves for two reasons. One is we shine light, not really light, X-rays, into them in order to characterize their structure. So we put in waves, we want to know something about their properties, we'll use Fourier transform. And the second reason, what other kind of waves are you familiar with? Acoustic waves. And unlike a gas where when we heat it up, the atoms go in every which direction independently, in a lattice, if I add heat into the system, the atoms want to move, but they can't move in any direction. They are bounded by the lattice. So you have what you have instead of just free motion due to heat, you have phonons, acoustic waves in them. So that's the second place. And we have a third place where we'll run into waves in lattices. Like we said. Guys, all of you finished quantum mechanics, I hope. Electron waves. Electrons in a lattice behaves like waves, and all electronic properties of metals and insulators come out of the behavior of waves in a lattice, electron waves, quantum waves. So we need it across the board, the Fourier transform of a lattice. Okay, so let's see how one defines it. So it comes under the name reciprocal lattice. Actually, one of the few times that the Hebrew term is shorter and more concise, Saligofri. And the wave vector of the reciprocal lattice has to follow the rules that I'll give now. Let's stop a minute and look what's written here. Okay, why do I say that vector k defines a lattice?
It's like R.
It's exactly like R. It's a vector. So this vector describes all the points in the reciprocal lattice. Okay, since I have vectors, k dot r is just some point r in the lattice, not necessarily a point of the lattice, but if I shift it by r, I go back and get the same value. Why is that true? That's a symmetry. That's exactly the symmetry of a lattice. I go to another point. Not necessarily a point on the lattice, another point in space, which is at a distance of r, large R, capital R. I have to see exactly the same behavior, because that's actually the magic of a lattice. Any point in the lattice is the same as any other point. So I can't get a different behavior. So I'm looking for the vector that gives me this property. Okay. I write down what is this vector. Again, if I started with a three-dimensional lattice, I'll have also a three-dimensional reciprocal lattice. And since it's a lattice, it has to follow this construction. My only problem is to find what are B1, B2, and B3. Okay.
A2 and B2 in the bottom. Shouldn't be A1 dot across A2 dot product. No, the first one, B1. No, B2.
B2?
The denominator.
Same thing. Yeah. Okay, let's see that it works. I wrote down the solution, but we should check that it works. What is the condition, basically? The condition is
K dot R, step by.
J pi has to be equal to 2 pi. If I fulfill this condition, this is automatically fulfilled.
It's times delta quadrant, right?
Okay, so let's see that it works. Let's check the delta first. Okay, this tells you if I is not equal j, it's 0. Yes, but let's say if I take b2 and multiply it by a1 or by a3, I have a1 or a3 in the cross, so it's perpendicular. This cross is perpendicular to a1 and a3, so if I have a scalar multiplication by a1 or a3, it's equal 0. Okay? Just from the cross properties. So what is left? Let's look at, let's say, a1 dot b1. Trivial. Okay. And since I can rotate the order here, then it's correct for anyone. Okay, then So far, so good. And since this is a multiplication of 2 pi by an integer, it's equal 1. So my definition of the vector k, the reciprocal vector, gives me what I want. Okay. What is the reciprocal of the reciprocal lattice? The original one. Let's do an example. So, let's take a simple cubic. Okay, I've written down the 3 basic primitive vectors. Okay, let's, assuming you don't remember anything about cross products, I'll write it once. Okay? So what is it?
1 over 8.
The volume of the lamp.
2 pi over 8.
The volume of the primitive unit cell. And that's always right, not just for simple cubic.
That's also the area of the,
Excuse me?
the one on top, the cross product is the area, it's also an area.
It's the area of the basis of
No, not the A.
mhm. Okay, so now as usual with a Fourier transform, I started with something that had units of length, A, and finished with something that has units of 1 over A. Like as usual. Okay, so the reciprocal lattice of a simple cubic is also a simple cubic. Okay, let's do another one, a bit more challenging this time. Okay, everyone has it written down. Okay, before I go into more how do I do this calculation when I'm only in one-dimensional or two-dimensional systems? I'm mentioning it because I have this tendency to put such questions in the exam for the simple reason that two-dimensional or one-dimensional lattice are simpler. And for some reason, students start to try to feed this, and they don't have 3 vectors. And after catatonically staring at the page, at their exam for half an hour, they're coming up, but I don't have 3 lattice vectors. This construction was needed because 3 dimension is more complicated. For 1 dimension, 2 pi over A, I don't have any other structure. I'll let you think at home what happens for 2 dimension. For simple cubic, I can have something. Okay, FCC. Okay. The same procedure. Oh, so I have minus here and I have a minus here, I get plus, yeah.
If we have a problem in 2 dimensions, can we like add another axis orthogonal to the axis and maybe solve the problem?
That is also a way, but you have to remember to drop the third vector.
Yes, but we need to choose. How do we choose the
Perpendicular
The
to
cross
the...
product.
Yeah.
The cross product of the two vectors you have.
Yeah,
Okay.
exactly. 2 and y. So it's minus, the first one is minus, the second one one of them I missed the minus, let's see.
plus
The last one I have here,
that is plus?
this is plus what? So it's so
זה לא כל אחד מהמכפלות האלה בכיוון אחר כאילו?
Yeah, all of those are
I'm doing A2 cross A3 because that appears in each one.
כן, אבל סל וקטור.
מינוס A בריבוע חלקי 2, X אחד.
Oh, sorry. And now A1 That's why units are so important, and checking this is a vector, so I had to end up with a vector. So even if you're sloppy like me, you can check that your result is wrong. Okay, so here we have a over 2 y plus z dot x has no partner, so it's 0. And I have here twice a over 2 cubed, so it's a cubed over 4. Okay? So now I go and let's say calculate B1. I'll continue here. Okay, and I can go and do the same for B2 and B3. And someone recognizes these vectors?
BCC.
It's BCC. So the reciprocal lattice of FCC is BCC. So the reciprocal lattice doesn't have to have the same structures in the original one. We had it for simple cubic, but it's not generally true. So BCC, please complete at home B2 and B3.
Isn't it just the same thing, but it's cyclically about 8 points?
Well, it's not the same lattice. We know that the number of nearest...
No, I mean like B2 and B3.
It's trivial, therefore...
8, 1,
Right, so you'll have the same structure with the minus going to y and z. But once in your life you should do it just to gain confidence. Yeah.
The three types of lattices we can form any possible.
No. There are. It's a whole field in mathematics/physics, which is known as crystallography.
No, I mean.
You have 14, if I'm correct, 14 different structures of lattices that are divided into 7, if I'm correct, I already don't remember, it's 70 different subcategories of lattices. You have that can appear in nature. So it's a very rich field. It's actually same that you have condensed matter physicists or quantum physicists, you have crystallography. It's a whole field. So, as I said, I would have, if we had time, I would have given a couple of more examples, but at no course all of them are covered. Google it, check textbooks. Ashcroft has these descriptions. I perhaps didn't mention in the first lecture, although it appears on the website of the course. I'm following Ashcroft as a textbook. Solid State Physics is the name of the book. And I'm not following necessarily the order that it appears in Ashcroft, but everything that I teach appears in Ashcroft. You have to dig up a bit. If you have questions, I'll give you the chapter if you have problems finding it. Okay. Generally, in the reciprocal lattice, the volume is 2 pi to the power of 3 divided by the volume of the original lattice. A bit terminology that
How does that work with units? Or it's not supposed to?
it works lovely. If each unit of length becomes 1 over a unit of length in the reciprocal lattice, so the volume is 1 over unit of length to the power of 3.
It's not it's not the same kind of thing that as we picture a left, because the units aren't length.
They are 1 over length. Look here, you have 2 and 3, so it's units of 1 over length.
I mean geometrically.
So it's in reciprocal, it's in K space, not in R space. You should have been already familiar with it from Fourier transform. What was length becomes 1 over length. Okay. A couple of more definitions that will become useful for the purpose of this lecture, which is basically saying something about shining light into a lattice. Okay. One of the most basic concepts in lattices is lattice planes. You have seen it yesterday when you looked on the quartz and you got nice planes that jump to your eye. Okay, so let's see an example for the easiest two-dimensional case that I plot, which is a simple cubic in 2 dimensions. Okay, so what is a lattice plane? This is, for example, a lattice plane.
Just a straight line across the...
Well, a line for 2 dimension, a plane for 3 dimension. Right? It could be. That's also a plane. Well, this is also a plane. You have an infinite number of planes. And take 2 to here and 1 to here, and another plane. An infinite number of planes. Right, they go through all of them go through points. They don't go over all points because they're a plane and not a volume. But they cut through a family of points. And now you would like to give them names. Well, you can always wave your hands, but that's not the most efficient way to describe a plane. Oh, that's the plane, that's a plane, that's a plane. Okay, so you want to give them names. So I'll just declutter what's happening here. So, what's the easiest way to give them names?
By the perpendicular bit.
Exactly. So, I have a vector that points to the next plane of the same family.
What? Can you say it again?
I have here a plane. It's a line because I'm drawing it in 2 dimensions. I have a vector that is perpendicular. The vector can be of any length. But let's say I'm choosing it at the length of the distance okay, but that's not so convenient. What would be the most convenient way to describe it? Because how do I get perpendicular?
Vectors.
Cross. Right? Cross between 2 vectors give me the third vector.
That's how the lattice...
Hmm?
So finding the dimension -1 vectors of the star lattice? Okay.
Would be a reciprocal. Because we did it actually, if you think about it. We wrote down 3 directions, A1 cross A2 and so forth, so it's easy to use that definition. So I have a family of reciprocal lattice vectors that are 2 pi over d times the origin times the reciprocal belonging to the reciprocal vector. Okay, how do I prove that this is correct? So let's assume I have a vector n which is perpendicular to a plane. My claim is I have a reciprocal vector. K here is a reciprocal vector. So how do I prove that 2 pi over d times n perpendicular is a reciprocal vector?
It's better formulas than just you describe it as a cross product of 2 vectors that are within that line.
What is the condition that a reciprocal vector has to fulfill? E to the power I k dot r equals 1. Right? That's the condition. Okay. Each one of these R's belong to one of these planes, right? So all the guys that are on the plane, E times IK, which is perpendicular to the plane, is 0, right? So all that remains is the difference which is perpendicular. And that is always 2 pi over d, which gives you 2 pi here. So I know that a perpendicular vector to a plane has to be a reciprocal vector. Okay. So all this I need for the definition of of a Miller index, and the Miller index of a plane is a plane that is perpendicular Okay, so what does it mean? I'll give an example here. Okay, A1 is AX, A2 is AY. So how do I call this plane?
Two-dimensional cubic, single cubic.
Yep, looking at this. The Miller index are numbers.
1, 1, 0, 0.
Well, I have just two, so I don't need
So 1,
1, 0.
1, 0,
1, 0.
1, 0. Why? Because the perpendicular, well, 0, 1, sorry. Let's choose this as X and Y. The perpendicular vector is in the Y direction. Let's use another color. Right. Let's use blue. One.
Or is 1 and minus 1?
Right. Minus is no, sorry, it's the other way around. Minus 1. And so on and so forth. So the gallium, sorry, it was germanium lattice that I gave you yesterday that had a flat space. It's in direction 1, 1, 1. It's cut in the direction 1, 1, 1. So it defines me exactly where along the lattice that constructs it, it's cut.
Which one was it again?
This big black piece of germanium. It was a cylinder with a flat face. The flat face was there in direction 1, 1, 1. Why is it important that 1, 1, 1? In a moment we'll see it clearly defines the distance between the different planes.
You could also say about that blue plane that it's 1 minus 1.
It doesn't make.
So, an linear index is the indexes of the vector.
And the NLM, you can tell me, but if I multiply all of them by 2, it still will be a perpendicular vector. That's why this long is the shortest.
So I can think about it like the vector to the closest plane.
Exactly.
Okay.
Well, in reciprocal
Yeah.
space. Okay, so I gave you a mathematical background. I'm describing you all the time that lattices are atoms sitting at lattice points. How do we know it? So, nowadays you can take something like a scanning electron microscope, which is basically a very thin needle, mostly conducting, and you try to pass current between this needle and the surface of, let's say, a lattice. And if you're exactly on an atom, the current is usually larger. If you're in between, it's smaller, so you can just scan it and get a picture of the atoms. Well, that's the surface. It tells you something about the surface. It doesn't give you information about what's happening inside. That's today's technology. Lattices were known already in 1903, 1904. Yeah.
You can maybe try to scatter.
Well, the next answer is you scatter some wave off it. Now the question is, what should be the wavelengths of the waves that you're trying to scatter off it? It depends on the distance between the atoms. If you remember in the previous lecture, I wrote some typical distances. All of them were in angstroms. So you need a wavelength of a few angstroms, which is about a few thousand times shorter than visible light. So visible light won't help. You have to go to shorter wavelengths, higher energies, and these are X-rays. So until X-ray wasn't discovered, no way to measure properties of atoms in a lattice. Yeah.
But you have רגע תקיפה, כאילו שאתה יכול לראות עליו עם לייזר וזה מפצל כבר בעצמו, שזה לא קשור
What is the length scale, wavelength of a laser?
red laser, so 500 nanometers.
5,000 times larger than an angstrom.
No, but you have things that the typical length is invisible in light, not always.
No, what if you look on the gratings that give you interference in lasers, what's the distance there?
About hundreds of nanometers.
Right. So again, it's the same scale. There's a Russian proverb that tells you small stones don't stop big ships. If you have a very large wavelength, it can't see small things. It's not seen. You have a microwave at home. You can see what's cooking in it. You have a window, you see what's cooking in it. But it has also electromagnetic waves there that are hot enough to melt your face. So why, when you're looking at your microwave, your face doesn't melt off? If you have a Faraday cage, why do you see through it? Right, because you have there a grating which is of order of millimeters, which is relevant to radio waves that exist, microwaves that exist in this apparatus, but much larger than visible light. So you see the visible light that stops the longer wavelengths that heat up the whole thing. Everything is a question of scales. So in order to see lattices, you have to have something of the scale of angstroms. Therefore, you need X-rays. So until you knew how to produce X-rays, you couldn't measure anything. Okay, so
איך מה שאמרת על המיקרוגל קשור לפליין שאמרנו?
Well, I was asked what is the connection between the story I gave about a microwave to diffraction of lattices. The only connection is scale, meaning that you have to be in the right wavelengths in order to go through the system and see its details. If the wavelength is too long, in the microwave it's whatever, millimeter, centimeter wavelength, they don't pass through the grating, but visible light does. Same thing for if you want to see properties of a structure that has a distance of a few angstroms between its constituents, you have to have something of wavelengths of order of a few angstroms, which is X-rays. That was the whole point. So what are you doing in an X-ray experiment? You take some lattice, some piece of material, you shine in some X-rays at direction K, meaning I have here a plane wave that comes into the system. I put a detector at some direction K prime and measure, that's supposed to be a detector, and measure the intensity at that direction.
Why would you not put it after the material? למה שמת את זה כמו שזה?
Okay. So first of all, that's the reason I brought these two sticks, just to demonstrate. Here it looks that I can move it only at one angle if I'm plotting it on a two-dimensional board. But the possible directions is huge. I can put in my wave here and measure exactly. I have the whole area of possible directions of measurement. Now, why do I measure it in a direction which is not in and the other direction out? Because anything interesting about the structure is return of light that didn't pass through. Right? If I have no lattice here, right? What do I expect to see? Everything past it. Right? So that's not interesting. It doesn't teach me anything about what happened here. Right? The fact that I'll get some scattering in other directions, that's already interesting. Actually, they never stick here a detector because, look, atoms are very small entities and their scattering is, at the end of the day, quite weak. So the whole power of the X-ray, most of it just gets to the other side. And if you put a detector here, it's like trying to take a photograph of people against the sun. You know that you don't get a good picture, and in worst case you burn your detector because you want something very sensitive and you stick it at the highest power. So not good. Yeah.
But what about like not a reflection, but a fraction, like about 10 degrees, but not in like 70, 80.
That's what I said. You stick in like at one direction. You put your detector at another direction.
Why not much like?
You can do it all over. You're at liberty to do it in any direction. You can even gather information at a bunch of directions. Let's say if you put here some materials that's sensitive to X-ray. Don't know how many of you broke their hand or leg at the time where it wasn't digital photography in X-ray machines, but good old photographic plate. Then you stack your hand or leg in the machine, and you'll get a negative like in the old cameras. Would come up and take a picture. You have a whole spread of directions, and you photographed it. And you have different experimental setups. You can move perhaps the detector. Perhaps you can rotate or move the sample itself. It has the same influence. You change K and K prime in relation to the lattice that way. So basically, the whole thing that I want now to pull out is if I'm putting in a wave at direction K and putting a detector at direction K prime, what is the intensity that I'll measure? It won't surprise you that for almost all directions K prime I'll see nothing. But the interesting point is, where do I see which is not trivial, not just going through the system and that's that.
אז אם
Okay, so two people formulated the mathematics regarding this in 1905, 6, 7, I don't remember exactly when. Couldn't be before 19 or 1898 when the first Röntgen picture was taken. For that, no way to do it. Okay, one of them is Bragg, that did it in Cambridge, England. And the second is von Laue, which did it in Berlin. Both of them ended up with Nobel Prizes on it. Bragg was the first to perform it, but his mathematical description is less convenient, less general, but I'll give it for historical reasons. And I'm mentioning von Laue here first of all, because we'll use his formulation, it's more convenient. And since it's the day of memorial to the Holocaust today, von Laue was the only member of the Prussian Academy of Science who voted against kicking out Einstein from. So the guy had courage. So we mention all times bad people who did things, but this guy was, Einstein called him after the war the only decent German scientist that was left in Germany. Okay, so let's see first. Bragg is also an interesting guy. He headed the X-ray laboratory for many years in Cambridge. What's interesting about him? His son, not surprisingly, also called Bragg, also got a Nobel Prize, and on X-ray scattering. So it's interesting to.
It's in the family.
It's in the family there. Okay, so Bragg took very seriously the description of planes. Why? Because the point that you mentioned, it's like a mirror. And asked, what will be the connection between coming in at K and going out at K prime that will give me positive interference? So let's see what he did there. Okay, so I have two planes. I have a plane wave coming in K. It's supposed to be parallel. So it's coming in at theta, going out theta, like the usual case of a mirror. And what is the difference in the optical way? These two parts, which are D if I call the distance here d, so that will be d,
2 times d sinus d.
right? So if I know the distance between the planes, or I know lambda, the wavelength, that's the more relevant case. I know the wavelength of the incoming wave. I know at which angles I get positive interference. I can tell you what is the distance between the planes. So I do an experiment, let's say rotate it at different angles and get the plane structure of the lattice.
Can you explain how do you get the wavelength here? Why is it? Why the wavelength is appearing here?
Because I need the phase accumulated across it to be 2 pi, or some multiplication of 2 pi. Right? That's it. Okay, so that's the Bragg description. Very intuitive, but hard to see what happens when I'm in 3 dimensions. You have to start to think, what are all the different planes that I have here? How are they related to K and K prime? Not extremely easy.
You said so the reason the added length is equal to a multiple of the wavelength is because you want there to be no phase change, or a multiple of pi, right?
Multiple of pi.
Why is that? Like, I can imagine 2 rays going in the same direction with a difference in the phase.
Yes, but you want to have here constructive interference.
Oh.
That's exactly so. When you, I'll stop a minute and emphasize it because it's important. At the end of the day, most of the wave continues on. It's only a small portion of it is reflected from the first plane, a small from the second, and so on and so forth. So if you want to see what's the wave coming out in this direction, you have to add them all. And you have to add them in phase in order to get a signal that is not 0. Yes?
Is there a good reason we look at the angle between the, like, not pi minus theta and theta? Because usually we look at
That's
You can switch between sine and cosine.
yes.
whatever you feel comfortable with. As I said, that's not the formulation that we'll use. There's a more elegant, and that's the von Laue description. Okay, von Laue forgets about planes. You don't have planes in the lattice. You have points, right? You are scattered of the atoms, not on a mirror that reflects something. So his point was, look, let's look on 2 points that scatter the incoming wave. And let's say there's a distance d between them. So I have my plane wave coming in at distance k. And just for my convenience, I'm drawing it in right angles. It could be any direction coming out at k prime. Okay, this is the additional path that the guy scattered from here does compared to this one. In order to get constructive interference. I remember that multiplying d by k gives you this length, by k prime gives you this. And since k is in one direction and k prime is in different, you have minus. So, and what's nice about it that this is, you don't care about angles and stuff. It's just 2 vectors, the incoming and outgoing vector.
So, to understand the plane structure, just...
I don't have a plane structure. I have just 2 points.
Oh.
Because scattering happens between 2 points. Now, the nice thing, what is this d? Any reciprocal wave function, any lattice vector that exists in the system connects me between 2 points. So I'll erase D and write R. So, and what is this? The condition for a reciprocal wave function. Vector. So I replace this. Just not to get confused, I'm writing here G instead of K. And G is a reciprocal Okay. Okay, so all I need to know is whether k minus k prime is a reciprocal wave vector. Yes, you'll have positive interference. No, will be 0. That's it. And this is a very elegant way to describe it, for me much easier and intuitive than planes. I don't have planes, I don't have mirrors. So at the end of the day, all you have to do, give me k that comes in, give me k prime that goes out, subtract one from the other. Is it a reciprocal wave? Lattice vector? Okay, you'll see interference. If not, no. And now, if I'm taking some incoming wave and putting my detector somewhere in space, the probability of seeing something would be quite small. No, just because the reciprocal vector is points that have a distance 2 pi over lambda between them. Now you also understand why you have to have X-rays there. Because what is the scale of G? 2 pi over A, roughly speaking. If lambda is much shorter or much larger than A, I will never hit this condition. Or I'll hit it all the time if lambda is, so I won't see the interference. I have to be of order of A in order to see the interference.
Sure.
Yeah.
I don't quite understand why this equation is true.
Okay. What's k times r?
K is the projection of one over the other.
No. I'm interested in this distance and this distance, right? This is the additional distance.
Okay.
So k dot r is this projection. K prime is dot r is this projection, and they are in opposite directions. This goes in this one. This is incoming, this is outgoing. So it has to be one minus the other.
It's probably simple, I think.
No, you want to see it, just put here a theta and start calculating the length. Once you have theta, you can write down the scalar product between k and r, which is these things, right? Okay, so lovely. What do I need more than that? Well, I need two things that I'm still missing for a real lattice.
Conservation of energy. Because this light.
Conservation of energy is that the wavelengths of k in and k out is the same.
you need to add this condition. It's not, כאילו, למה זה ברור מהמשוואה הזאת?
Because
אחרת. זה תנאי נוסף.
ויכול להיות שיש אחר, שהוא בלע חלק מהאור וחלק מהאור הוא לא בלע. כאילו מה עם צבע.
יוסי, אני עוד בשיעור. As when I'm writing down K and K prime, I'm assuming we'll do it in the next lecture for a specific example. K and K prime are the same wavelengths. Why? Because this is elastic scattering. Why is it elastic scattering? The wavelengths of the X-ray is very short. It's very energetic. You know the spectroscopy on atoms you do on visible light, more or less, infrared visible light, because that's the typical distance to excite an electron. To excite an electron with X-rays, you kick it out completely. It's very improbable. So you don't change the energy of that. So it's the same wavelengths. We'll do examples for this in the next lecture, and also discuss some interesting things that we do with X-ray scattering, and that's for the next.